I'll just take a moment to welcome all of you to the first offline event by Google Level Student Clubs at RCCIIT. I think this is the first time a lot of you are entering the auditorium, right? Yeah, and like I entered the auditorium for the first time when I was in first year. We had our induction here, and but this is also the first time for me standing on the dais here and addressing all of you. So that's we're both having first today. I'll just introduce to all of you our speaker for today. It's Preetham Ghosh. He is an alumni of our college. Basically, he is an SD at Accenture and an IoT and robotics enthusiast. And he's also personally mentored me when I was in first year. So he's like I've sat with him and I've learned how to do DP-DP switches and stuff. So yeah, this is going to be amazing. I can promise you that. And one more thing, that since all of you have registered for it and have come here to attend, stay for the whole duration of the event. I don't want to see people leaving in the second half. That is not something I want to see. Okay? A lot of people wanted to attend this event, and you are the ones who could. So please make it count. So with that being said, I'm going to hand it over to Preetham. Preetham, you can take it from here.
Thank you for handing over this event. As Shrupadeep mentioned, I already mentored him in multiple projects, I think, of which he has gained quite some percentage of my knowledge, which is also not complete in my sense. So let's start with this event. Let's get accustomed to some basics of the electric circuits related to robotics, because we'll be talking in depth regarding these concepts further in the event. So from the slide visible, how many of you have got idea about capacity of batteries, any measurement of batteries or anything? Would anyone like to add to this? How would you measure a battery? Anyone? Anything, doesn't matter if it is wrong or anything. No? No interest? Okay, so I think many of you are using Android phones. So when buying an Android phone, you check that the capacity of the battery is written as 5000 mAh. So what does mAh stand for? It's accounted for milliamps hour. So it decides what amount of current a battery can deliver in a specific amount of time. So by that, it can be decided according to our projects what type of battery should be used and what the prototype suggests for the power requirements to be. Wattage is just the electrical power consumption unit, so multiplying volt and ampere you can get the wattage. That also decides the power of the battery. Capacitors and diodes, before coming to those, can anyone add to what are active and passive components, if anyone is accustomed to that? In electrical, what are active and passive components? Anything? Ohm's law? You definitely went through somewhere in between class 7 and 10, I guess. So let me add to this. Active components refer to those which actually contribute to the electrical circuit with some power and active participation by involving influencing the voltage in that circuit, be it closed or open, or manipulating the current. Those can be called as active components, like capacitors, batteries. Inductors can be to some extent because they contain the inductive energy, which in turn turns to electromagnetic energy, whatever. So that's a bit of in-depth. I'll try to avoid those for the time being. Next is diodes and resistors. These things add to the passive component because they don't actively manipulate the power supply, electronics, voltage levels and the current flow. They just act according to the current flowing through the circuit and influence the circuit passively without changing the potential difference in that circuit. Moving forward from that, let's have an idea of series and parallel in circuits. So both batteries, power supplies, and passive and active components can be connected in a parallel and series configuration. From the illustrations present in the slide, can you all brief me about what difference do we have in the series resistance and series battery configuration? Can anyone point out from the slide? Anything? What difference do you see, like when two resistors are connected in series, or two or more resistors, and when two or more batteries are connected in series? What is the difference in those? Anything? Guys, you need to participate. Maybe it is the first event, or maybe you're seeing me for the first time. Doesn't mean that you'll go dumb and all. Yeah, if someone raise their hand. Give him the mic.
No, thanks.
Take the mic, take the mic.
Yeah, what's your name first?
Hello. Hello.
It's fine, just.
Just be a bit loud and clear, we can hear you.
Answer.
Always check the mics before the event. Just typical technical glitch. Every event organizer.
In series connection, the current through all the resistors are equal, and in parallel connection, the voltage through all the resistors are same.
Yeah, sure. Anything else? And what about the batteries? What is different with parallel and series batteries?
Battery noise.
You can try from the resistance definition only. What you said, in series the current is same
Yes.
and the voltage will be different,
Yes.
right? So same applies when connecting batteries in series. The voltage of the batteries can be different, but altogether they can supply one single current. The value of the current will be constant throughout the closed circuit, right?
Yeah.
Okay, so coming to the parallel part, you can sit down. The current through the resistors varies, but the voltage remains constant. On the other half, while connecting the batteries in parallel, you can see the voltage remains constant and the current multiplies. If two batteries of the same capacity, say you can see from the figure that when connected in parallel, the series connection gives the current I and the parallel connection gives the current 2I. So the current will be multiplied by whatever the factor the battery holds the voltage above. So if the batteries are of the same capacity and same voltage, the current will be doubled, and if one is of the half capacity and same voltage, the current will be halved, and so on. It can be calculated from the Ohm's law itself. Not exaggerating much about this battery and stuff. Next, power supply can be of different types. Like you can require a small burst of energy in the circuit to get it jump started, or a constant flow of energy that we already covered about the batteries. So a capacitor, or rather to be specific, a supercapacitor, the one on the right, blue color one, is a supercapacitor. So that is actually of low voltage and high capacitance. So what do you understand by capacitance? The ability to hold the charge for a small amount of time and deliver it all at once with high current draw. So these supercapacitors can be used in appliances where the battery weight needs to be managed and the same amount of voltage and current can be supplied by that rated capacitor also. We use this in case of very micro projects which cannot actually accommodate any battery. In the sense there are multiple types of batteries which we'll come to know later in the slides. So in those cases the supercapacitors are used. Going on. So here you can look at what all types of batteries we use in prototyping and all kinds of testing in these minor projects that you are going to do. Probably you are going to do all these sitting at home and not participating like we used to do actively. We used to have technical events in college, inter-college events also. So there you are getting negative on the experience part, but you can still buy out these things and gather components, experiment, anything. So, is anyone accustomed with whatever types of batteries are shown on the slide? Can anyone name them, or anywhere they've seen, where they're used, what does it look like? Someone raise a hand, please.
Okay, so the lithium ion is used in remote controllers, I would say, and the lithium polymer is used in Android devices, and lead
Okay.
acid, I think I've seen it in UPS.
Lead acid batteries, right?
Yes.
You are partially right. Actually, lithium-ion batteries are not used in remotes or anything that you say in common appliances, because these are not your typical AA batteries. They might look like the same, but whatever you use, like the Duracell ones, Nipo, Eveready, these are not the same. Each of these cells have a voltage of nominal 3.7 volts. But when you use the AA batteries, you can go home and read the description on its body. It says 1.5 volts.
Right.
Okay, so these actually pack a way lot more energy than those AA batteries, whatever you use in AC remotes, TV remotes, and maybe game controllers, they also use that. Okay, so there you got to know that lithium-ion batteries are similar to lithium polymer batteries in case of voltage current. You can sit down. So lithium ion and lithium polymer batteries are almost same regarding to voltage levels and current dissipation. The major difference lies in the rate of current discharge, which is actually mentioned by a C rating, mainly found in the lithium polymer cells. So what it means, when a lithium polymer is rated, let's say it's 25C, a lithium polymer cell of 12 volts rated 25C at let's say 1000 mAh, you must be accustomed to that figure. So it can deliver a short burst of current which accounts to 1000 multiplied by 25. So it can deliver 25,000 milliamps or 250 amperes, right? That current can be delivered by the lithium polymer cell in one burst for a very short period of time. That cannot be accomplished by the lithium ion batteries. They actually lack in the current discharge property, but rest of the features are same. Both these need balance charging. Balance charging means when making a compound cell using the lithium ion and lithium polymer batteries, you need to charge each cell to a particular level, that it gets a separate charger, special type of charger for these. So every battery needs to be kept at a certain voltage for it to properly deliver current required in your prototypes. We generally use lithium ions in very small scale prototypes, like for instance some autonomous bots or maybe some IoT devices. Lithium ion can be used because these are easily affordable and the charging is not much of an action to be taken care of. But actually, what is going on in this? Can anyone take care of this? Just fluctuating internet. Nothing else. So bit of an interruption there. Let's continue. Lithium-ion cells can be easily available in the market, and their chargers are quite affordable. So when starting off with basic Arduino or IoT projects, you can easily buy these and make compound cells of your own. But on the other hand, lithium polymer cells are a bit on the expensive side, and they need a special type of charger for balance charging. Anything you understand about robotics?
Robots are just electrical devices which are supposed to help do certain tasks autonomously, or maybe autonomously, maybe. That's my
Autonomously or manually?
manual, yeah.
So let's categorize these into broadly two categories, manual and autonomous. So those two will be explaining and letting some light into in this seminar. I hope you'll find this interesting because a lot of things are coming up, so stay tuned for grabbing up any type of interesting or maybe some kind of boring information being thrown at you. Let's move forward. So robots are machines, as you say. So that needs to be moved, or it needs to move themselves. What do they use? What can be the ways of movement of a robot? What do you think they use? How do they move? Yeah, sure.
By using motors to convert electrical energy to mechanical energy.
So you're using motors, right? Yeah, correct. So let's generalize this term. Every robot or every kind of movement does not actually involve motors. There are different devices to achieve any kind of movement. Be it locomotion, be it rotational or revolution movement in a robot, we call them actuators. And these actuators are certain devices that consist of some or whole of moving parts and can be controlled using electricity, pressure, or any kind of external agent that is not directly related to the power supply, which is optional. So examples are given as pneumatic, hydraulic and electric. So pneumatic is basically working with air pressure. So it involves an air pump or compressor that can pass through forced air into the system, making the actuators work. Hydraulics use the same principle, but they use the medium as water or any kind of liquid which has some extent of compression so that it adds the flexibility to the system overall. And electric actuators are all around us, like motors, servos, chain drive systems, anything. So these can be treated as actuators. So what makes these actuators work? I mean, those are non-intelligent systems, right? They don't know. No, your hands and legs don't know how to function if you had no brain. Got me there, right? So for the actuators to function, we need some source of information or other signals for those to work and to follow certain instructions. For those, actuators needs to be controlled by something. So there are control circuits and sensors, modules, drivers. These actually get connected to the actuators directly, which in turn receives the command and signals from a microcontroller or processor that we'll also be covering henceforth. And likewise, the actuators move according to the signal provided to them. So the microcontrollers and processors act as the brain of the robotic system. So it can be as simple as using a logical AND gate, so which are already available in the market in front of ICs. And it can be as complex as using a standalone computer to generate signals. So standalone computers, have you heard of Raspberry Pi? Anyone? So it will be totally a new thing. I hope it will be interesting for everyone. We'll get into that. So the first thing, sensors. Sensors are devices that take in any kind of external influence or input into that and convert that signal into analog or digital response, passing it to the microcontroller or processor, which is processed by that, and in turn the microcontroller will trigger a driver or a logic gate to be as basic. So that will make the actuator work. So from the illustrations here, the accelerometer is deciding the orientation and position of a system if fixed with a microcontroller. And the infrared sensor actually acts as a distance sensing module or detects presence of light or dark patches on system. So these can be used in prototyping for proximity sensing, like if you bring a hand close to that, it will trigger a signal, or if you bring that module close to a dark surface, it will give a different value than compared to when brought in front of a light surface. So in that way, the output from the IF sensor can be decoded by a microcontroller and eventually triggered into an actuator through a driver. Next we come to controllers and processors, which act as the brain of the whole system. Be it autonomous, be it manual, you will partially needs some microcontrollers or processors to control its movements through the actuators. So when coming to the term controller, what comes up the first thing in your mind? What do you understand by controllers? Any examples, anything? What can you think of when you hear the term controller? Give me some input, guys. It can be silly.
Someone has raised that.
Yeah, give me the mic.
Controllers are devices with the help of which we can control any mechanical robot, or like pass a command to get a work done.
Okay, any examples on that?
Like if we control a drone, we have a remote controller through which we control the drone, how much distance it can fly or which direction to go.
So, have you already worked on a drone?
No.
What makes you say that complex a thing? Do you find drones interesting?
Yes.
Would you like to see a demo?
Yes.
You'll have to attend the full event for that.
Yes.
We might be having a demo, guys. I can't confirm, but stay tuned for that. Yeah. So controllers can be of that type also. So he mentioned a drone controller, which is way complex than what we are dealing with here. So controllers, or rather to be specific, microcontrollers are those integrated circuits or modules which can be programmed to some level using high level or machine level language through computers and different IDEs we use. So these controllers can actually take in signals from the sensor modules and convert it to messages or signals which can be interpreted by drivers. So these drivers actually in turn respond to the actuators. So those actuators can get the signal from the controller that this is the message being given to us and we have to work according to that. So it's just plainly your hands and limbs functioning according to the neural response from the brain. About processors on a broader aspect, don't start giving me computer specifications, Ryzen 5, 3rd gen, anything, or Intel. Can we have a vote? How many of you support Ryzen when coming to computer fields? Why do you support Ryzen? Anyone?
Better VRAM.
Could you please stand up? Whoever answered that. Give me 3 points. Why do you support Ryzen than Intel? Coming to advanced builds, don't go on to Athlon and E4500 builds of Intel.
It gives better VRAM inbuilt.
Mhm.
Then we don't have to buy a graphics card for normal low spec games, because graphics cards are quite costly nowadays.
Okay. And what can be the disadvantages of Ryzen?
It requires more processor refresh rate to run certain games.
That can be a processor limitation itself. I mean, you can't change once a processor is built to that refresh rate or clock speed, right? So you will eventually have to buy a better processor.
Yes.
Do you know Ryzen processors heat a lot?
Yeah.
Does that add to a disadvantage?
Yes.
But accordingly, they provide way more overclocking capabilities and multi-thread performance, right?
Yes.
So, you can say that was a good point. So there you get the basic idea about processors. So eventually it depends on the clock speed, number of cores present in that processor that actually acts as the brain of the system to drive the controllers with a particular clock speed, or which we call a baud rate while it comes to coding those. So these processors facilitate what type of appliances they are used in. Like the Raspberry Pi 3B Plus has a better processor than a Pi Zero. Both of these are standalone computers. I know that I am going a bit in depth about these, but you'll get accustomed to that. Processors actually define what is the core clock speeds and what can be the extent of processing power of a microcontroller. Let's get ahead in this. Coming to manual boards, which we added to as a category while differentiating between different kind of robots. What comes in your mind when we say about manual bots or manual robots? Don't take account of CSGO bots, which are mostly harmless, unless you are getting a all headshot on tough bots, whatever. So what comes in your mind when you talk about manual bots or manually controlled bots? What can be the examples? Manually controlled robots. Would anyone like to add? Anyone from the back? Is this getting quite difficult, guys? Can you understand whatever I am saying? Someone raised a hand. Two of them raised their hands. Both can put in some points. Yeah, what's your name?
Rajoshi Jangupta.
Yeah, say what do you need to do?
Manual robots examples can be mechanical arms in factories or storages.
So you are trying to mention any kind of assembly line or supply chain arms that help in packing in goods or
Yes.
putting the product in the proper boxes or anything like that, right?
Yes.
You're partially right, because those are not actually manual bots. They're actually controlled by a overall system, a bigger computer, which consists of a part of the system. Not totally right, but that can go on. Like one can use those kinds of arms to make their tasks a bit easier, like on a smaller scale. If you have that kind of an arm in a garage, you can get an assistance about lifting the car, right? Yeah. Anyone else? One was behind you. Yeah.
My name is Sambit Sarkar. Will train line switches?
Not exactly bots, but yeah, any kind of machinery or any interaction from the humans can be referred to as a manual bot, because we're not dealing with robots.
Yeah.
Yeah, that can be a point. So when coming to manual bots, the major point to be considered is how they move or how they react to the manual feedback, right? What can be the ways of locomotion, or rather movement of a manual bot? It can have wheels, which is quite popular or rather functional, better efficiency than any other drive mechanisms. It can be a biped robot, which walks like a human, or maybe it can consist of chain drive systems like tanks, may have flight systems like propellers, drone, someone mentioned here. So there can be multiple ways of locomotion and movement of manual bots, which is eventually connected wired or wirelessly to a human being holding a controller, using the controller to feed in directly to the brain if it is present, or even directly to the actuators, which can be the motors and servos and multiple other components. You just went through like hydraulic, pneumatic, electric, any kind of actuators. They can be directly controlled by the humans with wires or without wires, or maybe optionally with a brain or controller present in that. So let's come down to the basic and most effective drive mechanism, that is with wheels, which is the most popular used as well. So how do you think the vehicles and cars of our regular use drive? Do they have motors or engines attached to each of their wheels? Or what do you think, how a car drives itself? Are all the wheels connected to an engine? Yeah, say, someone raise a hand. At the back. With four-wheel drive, it is possible, but
Yeah, some have four-wheel drive, some have two-wheel drive, front wheel or back wheel, they are connected to the axis.
give an example of a four-wheel drive vehicle.
I think Tesla Model S or X is a four-wheel drive.
That
That's
definitely
why,
uses no, you are right, but any kind of SUVs or Humvees use a four-wheel drive, but eventually it's type of a differential and a four-wheel drive because their wheels turn, they don't have a dead axle configuration, right?
Yeah.
So that is eventually a differential and four-wheel hybrid, but yeah, that is definitely an application. So basically, four-wheel drive is a configuration when each of the wheels are directly connected to a motor or an actuator that helps to control each of these wheels individually or in pairs, which makes the locomotion a bit more sturdy than a two-wheel drive because it packs in a lot more power in that same volume or same configuration of the wheels. And it has its limitations because none of the wheels can rotate individually, so they have to work in sync with one other wheel on its side in pairs to be exact. So on the right, when you can see that is generally the chassis that we use for our prototype robots and any kind of rovers or anything that we are making. So these are very popular and available in the market easily. Doesn't cost much and has quite effective output. So as you can see, it consists of 4 motors and 4 wheels, each of these wheels connected individually to a motor and a battery in the center powering those motors in total. So what goes on here is 2 motors on each side are actually treated as one single side or one single motor to be exact. So has it been 2 motors, one on each side, or the one shown here with 4 motors, 2 on each side, the configuration would have been same. So in order to turn the wheel, you have to put different directions of rotation to the wheels, one on each side. So for instance, if that buggy or rover is considered, when the right wheels turn forward and the left wheels turn backward, which direction should the car move? Right wheels turning forward and the left wheels turning backward.
Right.
Left. Left.
Votes for right. Votes for right. Someone said right, I heard. It will actually go left. The direction of the wheels decide which direction the car will move. If the right side wheels go forward, the left side wheels go backward, the car will take a left turn. Eventually, if the left side wheels go forward and the right side wheels go backward, the car will take a right turn. This simple mechanism has been used by many applications for rovers and buggies which actually work on an autonomous basis. But this concept is used for its flexibility since every side can be controlled individually. You can also turn the vehicle right or left by rotating one single side of wheels or one single pair of wheels. So that makes it robust, and four-wheel drive is quite practical when it comes to autonomous and both manual and autonomous to be exact. But one thing, have you considered the weight of the system? I mean, even though it stays in the same form factor, it packs in way more weight required to move the vehicle. Is it not? because to move the vehicle on the right, you can see that it's quite a small prototype, and two of these motors have enough power to rotate it. What do you think? What are your suggestions? How can this be modified or made better? Would anyone like to add to this? Anyone from the right side? People sitting in the dark. Can we have some lights in the back? Do you think the prototype model on the right, can it work with two motors? 4 wheels but 2 motors. 1 motor on each side. What do you think will be the effects of removing 2 motors from that? Decreasing power can be a factor, but at the same time, we can add in the flexibility of having a 2-wheel drive and an axle configuration on the front wheels to decide the direction, instead of turning the wheels individually and using way lot more power than required. So that is achieved by 2-wheel drives, which we'll see next. So here you can see that the 2-wheel drive consists of one pair of wheels, either in the front or back, connected directly to the motor or actuator. So here a differential kind of setup is shown, which is generally present in cars and all modern vehicles. So what it does is, it leaves the hind wheels to be connected directly to the motor and it can move together, and the front pair of wheels acts as the agent changing the direction. So eventually it can be connected to a linear actuator or a servo motor which has a limited angle of rotation. So that can enable it to rotate in any direction it wants. And at the same time, the same actuator used for drive purposes can take the vehicle forward and backward. So that adds flexibility as well. So what are the advantages in a 2-wheel drive than a 4-wheel drive? Number 1, it makes the system light. Number 2, requires a bit less power than driving 4 motors for 4 wheels, or at least 2 motors for 4 wheels, because eventually one is used in a 2-wheel drive. And thirdly, it can have a more number of degrees of rotation, because when we have a rotating axle, you can add in more minute adjustments and the directions can be controlled in a better way. Moving forward from this, this is the most advanced type of drive mechanism. It's called a differential drive. If anyone has got any interest in automobiles, or you've seen different videos on YouTube or Facebook, there are examples where differential drives are explained and broken down into modules, so that every lever, you can see 3 types of levers present here. So every lever is explained in those videos. You can always Google these types of things. So not going into depth, the main point to be marked while explaining differential drive is, each of these motors, though connected to each of these wheels, sorry, my bad. So each of these wheels connected to the same motor can turn at different speeds. Even though connected to a single motor or a single actuator, it can turn at different speeds. So let's take an example. When a car is taking a left turn, which side wheel should rotate faster or rotate more? Right side wheel should rotate more. But at the same time, you know that that one vehicle has one engine only, right, to control the rotation of the wheels. So how do they achieve that difference in the speeds in the left and right side wheels? So there you have it. The solution is adding a differential drive system to that, so that every wheel can achieve a different level of rotation, different degree of rotation, while banking or turning to any side, even though it stays connected to one single arm pulley or one actuator. So there goes the advantages of differential drive over a 4-wheel and 2-wheel drive, where the former two are very much limited by angle of rotation, degree of rotation, the flexibility to rotate each of those in critical turns, or limiting the rotation of the wheels individually also. So next comes what can be used to move these wheels, right? They've talked about drive mechanisms. What does what? We have known. But you should be asking yourself that what exactly should be used to rotate these wheels, right? So has anyone here ever opened up an old toy or anything to take out a motor and simply connect it to a battery? That battery has also been salvaged from the remote itself. The remote was not working that day. Nobody knew that. So has anyone done that? Has anyone seen the type of motor, the first one, DC motor?
Yes.
Yeah, at the back. Kenny has the mic, please. Share your experience. What was that?
Actually, I took out the motor of the toy and connected it to the battery, and bought a small fan, that 5 rupees or 10 rupees fan, and attached to it the front end of the motor, and then it started rotating.
So when you first connected it, so guys, this can be the very basic grassroots level of innovation you get into while involving with electronics and motors and batteries. You get to explore these things, right? This can be one of your basic level understandings. You get to know how a motor rotates. You get to know that if you change the wires and connect it oppositely, it rotates in the different direction. So when you tell me, what's your name?
Swaraj.
So tell me, when you first connected, did you know already that which direction the air is going to be flowing while you connected the fan?
No.
So how did you troubleshoot it?
First
You wanted the air to come out from the front, right? You didn't want to get it to the back of the motor itself.
Yes.
So how would you troubleshoot it?
For the first time, I thought that the motor is not working properly, because at that time
Because you didn't have any air from the front. You thought that either the propeller is bad, or I need a better motor, or it should rotate at a faster speed, right?
Yes.
So guys, that's how you get into troubleshooting and noticing minute things. Like, it's very basic. Like, you connect a motor to a battery, it should turn. That's what electronics say, that's what physics says. But actually applying it to such a practical demonstration, like you did to yourself, that if the propeller is rotating one direction and the air is going in the opposite way, either the rotation of the motor is wrong or the propeller is itself defective, which is most of the low percentage cases. You just have to reverse the motor polarity. Change the terminals, yes, so the motor rotates on the other direction, and you get the air and you definitely call yourself electronics geek or anything. Like, you get the realization at that time. Yeah, sit down. Thank you for adding to that. So DC motors can be a major source of locomotion and movement related to robots. There are many different types of DC motors. I'm not going into details because, see, these, once you put in Google search that what are the types of DC motors, you can get an explanation. But this session actually aims at getting you accustomed to things which you would not find out generally. Like, there are people who never figured out how a battery works, or if you put the battery in the reverse order, it does not work. So these are the aspects that add to your experience and eventually will help to troubleshoot when you get into more complex projects. Coming to the next type of motor, it's called a servo motor. So has anyone seen this anywhere? These used to be present in toys where you used to have an RC car and it could only turn to one direction only. I mean, once you push it forward, it goes right. You pull it backwards, it comes straight. Then you again push it forward, it goes right only, because that servo is fixed with one angle only. It does not have a controller, it does not have a brain, so it cannot process what direction you want it to go. So it sticks to one angle, and when putting the forward input, it processes that, it detects that from the driver itself, and it sets that angle to the front axis. So what servo motors are, it has a very limited degree of rotation. What motors do, they go in circles all the way around. Like you can spin the axis, hold the axis of a motor and spin it to the full length. Those are used it already. So for servos, it does not happen that way. Servos have an inbuilt encoder that definitely needs a driver or a controller setup to work. You cannot control a servo. See, it has 3 wires coming out from that. A black, a red and an orange wire. The illustration might not be clear, but that's what it is. So conventionally you know that the black and red are positive and negative or reverse body say. Works both ways, just changes the direction of the motor. But while using servos, you have to take note of the polarity, or it does not have any reverse polarity protection or anything like that. You just fry the servo if you connect it backwards. So what the third wire does is, it takes the input from the controller. It's basically a signal pin that has a voltage level from 0 to 5 volt. So depending on the applied voltage, variable voltage will be applied to that, and according to that, it will decide to what degree the motor should rotate. So these are generally used in places of small degrees of rotation, like you need to turn a wheel to only some degrees. Like you need to go forward and backward on an arc so that it goes very minute angles. You need to implement in any kind of prototype or something like that. Next will be types of DC motors. So all DC motors are not those which you see in your toys or RC cars or anything like that. The first one is brushed DC motor, which is by far the most popular one. So these are just mainly used in small fans or USB fans you get, which you connect to the side of your laptop. You think it's fun, but eventually it will burn out. So these motors are generally used in that. It just runs off of a DC voltage, does not have any speed control or anything like that, does not have enough torque to drive a heavy RC car if it gets heavy by prototyping. So yeah, that is it. That is quite an application of DC motors there. And next comes geared DC motors. This is basically, you can see the front part in the illustration. The front part has quite some levers and gears and speed reducers to be exact. So any DC motor, brushed DC motor is taken and it is fitted with a gearbox so that the speed can be controlled to a particular RPM. RPM is rotations per minute, if you are not familiar with that. So to control the rotation speed of that DC motor, we use geared DC motors which have a certain ratio of reduction. It's not that every kind of geared DC motor looks like that. There are multiple types of geared DC motors, and mostly they have one geared compartment attached to the front of it so that it can have a different rotation for every kind of different gearboxes available. Next is brushless DC motors. So coming to brushed and brushless, what do you mean by brushes in a motor? Has anyone seen it? Yeah, someone is raising a hand. Can we have the mic?
Brushless motors have carbon in it, and brushed motors are magnetic.
Didn't get you. Can you explain that?
Those brushless motors, which are the brushless motors, are used in drones because they don't have magnets in it, and the
brushless motors don't have magnets in it.
Yes.
So how do you think they rotate? They spin
with the carbon.
I think you just say the opposite. While adding the carbon brushes, I get it what you are trying to say, but it's just the opposite. Brushed motors have the carbon in it. That's why there is a lot of friction and the motor gets hot while running for an extended period of time. Also, in a brushed DC motor, the solenoid is kept vertical to the magnets attached, right? But in brushless DC motors, same principle is used for rotation. But at the same time, brushes are not there and the magnets are arranged in way more dense way than in a brushed DC motor. So it has a continuous magnetic field all around it, and even without the brushes, by varying the magnetic field in the solenoid, the stator has the magnets and the rotor has multiple coils in it. If you have seen a drone motor or a brushless DC motor, you can see that 3 wires come out of that brushless DC motor. So what does that do? It is not an AC motor if you think that one is phase, ground and neutral or something like that. It does not work like that. But it has 3 degrees of solenoids or coils attached in it. So instead of having 2 degrees of rotation, which the brush DC motors have, it just has the north and the south poles alternate, right? But in the brushless DC motors, that timing to alternate the magnetic fields through the solenoid, that is decided with the 3 wires. It basically has a 3-phase kind of setup, which we will eventually get to know while studying these in depth. You can always Google it up. But what you said is, I'm just clearing it. You are totally right on that, but just the opposite. Principle is quite fine. You just have to get into the details. Yeah, thank you.
Thank you.
So brushless DC motors are generally used where you need to take note of variable rotation, a bit more precise variable rotation than brush DC motors, and it has to be efficient, relevant to a similar type of brush DC motor. Like if we take a 12-volt brush DC motor and a 12-volt brushless DC motor, due to the friction and heat of brush DC motors, the efficiency goes down. So definitely a brushless DC motor is way more efficient than a brush DC motor, and as you said, these are used in high-speed applications, drones, you can use in RC boards. Different RC cars also have brushless DC motors for a faster reaction from the controller itself. So, as we talked about geared DC motors, what is a gearbox? Can anyone add? What is a gearbox in general? Be it vehicles, be it DC motors, anything? Anyone got an idea what is gearbox? What do gearboxes do? You have seen gear shifters in manual transmission vehicles, right? I'm not talking about stick shifts. Whoever drives stick shifts, they can't drive. It's all done by a controller underneath that. You just have to pull that switch like you do on those racing simulators, right? So what gearboxes do, they add a certain configuration of levers and pinions. Pinions is also a kind of lever which is attached to the axle of the motor to bring down the high speed of the DC motor, which is unregulated and uncontrolled, to a controlled specific rotation for a particular specific rated voltage. So for instance, you can always go out to the market and buy 200 RPM motor and 300 RPM motor. If you take a look at those motors, the base of the motor is always same. The brushed DC motor is always same, only the gearbox will be different. It can look the same, but the arrangement of gears in that makes it 200 RPM from whatever 2000 or 5000 RPM. That's what matters. So gearbox is a system that reduces or rather controls the speed being attached to the motor head axle directly. So this can make the motor applicable to a wider spectrum of devices. I mean, you just can't get it off of a toy and fit it in some other appliance and wish it to work with the exact speed and accuracy you expected it. For that, you'll have to get a specific gearbox of a particular rotation or a reduction ratio. So you can see that gearboxes can both be decreasing and increasing the speeds. It's not always that it decreases the speed, it controls the speed to a particular value. So when we attach a step down gearbox, so let's say 20:1 is the reduction ratio. So what it does, for every 20 turn of the brush DC motor, the gear axle will have 1 turn. So this can also be stepped up, like there are 16 to 23 very odd ratios because as per the appliance requests. So these can gear up the ratio from a lower speed to a higher speed. That definitely requires a lot more power, and the efficiency decreases, but eventually it will be functional for the particular appliance that we put it in. Any practical examples do you think where gearboxes are used? I just told you what gearboxes do. Apart from vehicles, have you seen anything, or do you think you know anywhere that a gearbox can be used? Any handheld appliance, just a hint.
Watches and clocks.
Definitely, those some of the recent watches definitely has a gear system that's not directly acting on a motor. How do you think a clock works? Does it have a motor actually?
Some of them do.
Some of them do, but the age-old principle has been the vibration of a quartz crystal. That's how the company came in. Have you heard of the company Quartz?
Yes.
It's quite popular because of the accuracy the vibration of the crystal provides. That's how clocks used to work, and nowadays it has just encoded motors and controllers in it. So it definitely has a gearbox in it to control the rotation of the individual arms, right? Yeah, that is it. One in the front.
The
yes?
most common example of that would be a fan.
Fan.
Yes, the most common example of that would be a fan, because there is a motor and...
Fans has gearboxes.
Yes, I think so, because the more speed
The
of the
speed is
motor...
controlled, that's
Yes, that's why I thought that.
How do you control the speed of a fan? What do you have for that?
There are some switches that can be...
Regulators you have, right?
Regulators.
So, what is a regulator? What does it do? What do you think? Do you think it's like a stick shift? You put it from level 1 to level 2 and something goes click-clack inside the fan and it changes the gear to a high speed? Do you think it works like that?
There must be some device inside that lets it change, like regulators.
No, actually not.
Potentiometer?
Yes, actually, yeah. So that's where potentiometers come in. Potentiometer is basically the same thing as a fan regulator. It varies the amount of voltage signal going inside the device. So be it a 220 volt ceiling fan or be it any small scale fan for any prototype or anything, regulators are basically potentiometers that varies the voltage. It does not have a gear system. The most basic example can be a drill machine. Have you not seen a drill machine with the gearbox in the front? I mean, it definitely has a speed control. There's always good quality drill machines with a speed setting, a lower speed and a high speed, which we call impact drills. Right, you must have seen those. So that is a practical application of gearboxes. It has multiple levels of gear reduction so that when you press the button softly, it can still rotate at a lower speed. And when you flick the button and go all in, it can switch to a higher gear, higher speed and a lower reduction ratio. That's how it works. So, coming a bit specific to what we are going to achieve here, because this is not going to lead you to NASA or anything to develop Mars rovers from this level itself, though you can definitely aim higher. But we are trying to get into projects and prototypes which will basically inspire you to participate into more things from yourself only. In spite of events and whatever used to be in the colleges, which is now closed due to the pandemic and there are many other hindrances, you can actually implement projects and prototypes from the comfort of your home, get the supplies delivered to your place and try on experimenting. So has anyone seen this kind of switches before? If so, where did you see this? Any ideas what can be the application? Have you seen old radios? Old radios with a extendable antenna. They used to have a joystick like button which used to go from one middle position to one up and one down. That was used to select the channel or band, or switch between AM and FM. So basically these are DPDT switches. DPDT means dual pole, dual throw. From this one single switch, you can control the flow of electricity, rather the direction of flow of electricity from and to one device to the other. Like what happens when you press the switch of a switchboard, like your light switch? What happens then? You just flick the switch and the light turns on. But what if there were two light bulbs connected and you wanted to control them with one switch? Like I flick the switch one way and let's say bulb 1 gets light, power, and if I flick the switch the other way, the bulb 2 gets light. For these kinds of solutions, you need a dual pole, dual throw switch. This is just an example, the most popular one used. There are different forms of this. There's one switch that comes in a joystick format. So there's a stick type of formation. You flick it upwards, it takes the input. You flick it downwards, it takes a different input. That's how it works. So these kind of switches has. Let's get to the basics. How many poles does a one-way switch have? The regular switch that we use. How many poles does it have? It has 2 poles, right? So the convention goes, one will be connected to the positive, one will be connected to the negative. In the closed circuit. That is the basic concept, right? So in these kind of switches, you have 6 terminals coming out of this. So why 6 terminals? Basically it should be 4 terminals, but 6 are made in this for the convenience of usage, so that beginners like us don't short out the terminals and you do the full connection, you assemble the rover type thing, an alternate board, and then you just flick the switch and the battery got shorted. No one will be more disheartened than you at that time. So let's get into better wiring and better separation of positive and negative terminals. So that's why 6 terminals are pointed out in this type of switch. You can always check up Google for more details on these. If we have a demonstration of these, I can get into the details of wiring and what can be the directions of wiring for this. So that is it. That is basic. Like these can be used in practical when you make a alternate board or a rover type thing. You can make the board go forward and backward with one single switch. So isn't that cool? And you thought you would have 2 switches. Press 1, it goes forward. Turn it off. Press 2, it goes backward. That will be quite troublesome, right? So after this break, will you guys recover from the trauma that you just experienced related to manual robotics? Was that too boring of a thing? By the way, I mean, I just need some feedback. Any kind of. You can also let me know if I was talking whatever that was not making any sense. If it at all appeared to that.
Initially, the things were not making sense.
But yeah. Don't laugh on that, because these are quite some advanced things I'm going into. Because see, eventually you will get to know about these basics from Google itself. There are official documentations, and you can always gather resources from blogs and different articles. But I'm trying to put light on things that you won't find easily on the internet. So some very delicate things are being covered, maybe which we have gotten to know from experience by practical implementations. I'm trying to cover those points only. So let's get into the second half about autonomous robotics. Again, what do you think autonomous robots are? We covered manual robotics, which needs direct intervention of human beings. So what about autonomous robotics? How much of autonomy do they have? Anything? Any ideas? Yeah. Someone is raising a hand. Please give me a mic.
We code them earlier so that they can take decisions on their own.
eventually they are acting on some
Pre-coded.
provided information or decisions, right?
Yes.
So how do you call them autonomous? I mean, you are already feeding in whatever is decided. You are already providing a set of predefined conditions. How does that make it autonomous?
Like if it's a line follower.
Give an example, yeah, sure.
It's a line follower, then it will follow the specific path, but we do not know what the path is. We will code it so it follows the black line.
Yeah, so what you're trying to say is it has capabilities of taking in external inputs through sensors or any kind of interface. They interact with the external world to take in inputs or signals or any information that they are going to process against the predefined set of information.
Yes.
That's where autonomy part comes into robotics, right?
Yes.
Yeah, that is right. So what you just mentioned, autonomous robots are basically working on some predefined set of informations which are eventually fed by human beings while programming them either externally by using a programmer or a laptop or computer system, anything, or during manufacturing some conditions, some set of data fed into the registers and ROMs present on the controller itself. So that way the robot knows what to do when it comes across a particular real life scenario. For instance, what he just mentioned about a line follower robot. So you don't know where the robot will be applied, right? Whether it will be a black line on a white surface or a white line on a black surface. So the robot should have some decision making algorithms present whether to choose the former or the latter. So that will be decided with the help of sensors that is directly connected to the microcontroller, the brain of the system present in the robot itself. Moving forward, so we already discussed a bit on microcontrollers previously. So going in depth in this, what microcontrollers do, they help in take signals through the sensors. What sensors are? They act as an interface to the outside world from the external to the internal of the software of the microcontroller. So be it the software is being used over an IDE or it is pre-programmed or it needs to be flashed with some kind of file, zip file maybe for instance. So it is similar to the thing that when you do with Android phones, you root it and you install a different kind of operating system. Are there any Android geeks like that? Anyone ever tried to flash something, some other operating system into your Android phone and eventually it turned out to be a brick? Yeah, so can you share your experience? Anyone? Yeah, I'd like to listen from both of you.
Well, I tried to flash a custom ROM in an Android phone, and for that I searched in Google and followed the steps, but I think there was some problem. I did some mistake and my Android was like Android brick and I could not be used it.
Eventually it was not recoverable, or even if it was,
it got stuck in a boot loop.
Yeah, so it got stuck into a boot loop. So tell me one thing, when you looked up the internet for that custom recovery file or custom OS, what parameters did you check or what parameters should you have checked before getting the OS file?
Well,
basically
the first step was it was said to unlock the bootloader. Then
no, I'm not talking about the steps, I'm talking about compatibility. So how do you know a particular set of instructions, or in a broader aspect an operating system is compatible with a particular piece of hardware? You have to match it up with the architecture of the processor, right?
yes.
So you cannot run a 64-bit OS on a 32-bit processor or chipset.
Yes, that's
right. So that's where you face the boot loop or likewise problems, getting stuck into the loading screen only, or not being able to unlock the phone at all. So there it goes. Thank you for sharing. Someone else was also raising a hand. Anyone among the volunteers, I guess?
I was planning to change my phone's ROM to de-Google my phone. So essentially, I went through Google and tried to figure out how to do it. First step was probably to obviously, unlock the bootloader itself and flash a boot recovery thing. And then I was trying to figure out what ROM would exactly work for my phone, its model and its particular processor. And once I figured that out, I downloaded that custom ROM image and flashed it into my phone and everything.
So that was working fine after flashing, right?
Yeah.
So tell me one thing, why would you like to change the operating system or any kind of set of information for a particular chipset or anything?
Okay, so in my case, I think I already mentioned one of the ideas was to de-Google my phone. I was gonna try living my life without Google. Second was I was tired of all the bloat in my device, so I just removed it all over.
So basically, thank you for sharing. So basically, why we use a custom operating system or in a basic sense a set of instructions, we want to override some of the default features that the processor provides or some of the default instruction sets that the processor comes preloaded from the factory. Like for instance, when if anyone has bought an Arduino Uno from the market, basically Chinese clones are available all around. How do you know that that the Uno processor or the Uno microcontroller is working properly? What comes in default that you need to override to get it working? Or maybe whatever comes in default, how do you know that the Uno is functional? After you plug it in, then from the market plug it into the USB, what do you notice? What should be there that makes it functional? Got anything? Any Arduino Uno users? Okay, so the basic is the LED blink program. There's a default status LED in the Arduino Uno. You'll get to see one if we have the proper setup for that. So the status LED will blink once in each second. So 1 second it's on, then the next second is off. That comes default from the market when it gets packaged. So in order to load some custom program, you have to override that and upload a blank sketch and wipe all the default instruction sets present in that. Right? So this is where microcontrollers play a bigger role. Instead of any default information present, you can custom code it using an external coder, an FTDI module, or even over serial to USB. All these sound very unfamiliar to you, I know, but these are all interfacing mediums. Serial is an interface, USB is an interface, UART is an interface. All these are just names of interfaces that we use to interact to a microcontroller. These are quite in-depth informations. I'll try to explain as much as I can because this is quite a short period of time and we've got a lot of other interesting things upcoming. So basically, what is an interface? How many interfaces do you know in real life applications? Interfaces help us to communicate with devices or other technologies, right? What kind of interfaces do you know or are you familiar with? I can give you a hint, one can be Wi-Fi. Anything else? So by Wi-Fi we are actually interacting between two devices, right? So router is a hardware device and your Android phone or laptop or computer is another piece of technology. So Wi-Fi can be an interfacing medium. Similarly, Bluetooth can be one, RFID can be one, the same way you just swipe your Metro card, smart cards, that's working on RFID. So these are interfacing mediums. Similarly, microcontrollers need to be connected to an operating system to have a custom set of instructions loaded on that. So here the interfacing comes in either through hardware interfacing like USB or UART, connecting a cable from the microcontroller to the computer, or it can be wirelessly controlled through Wi-Fi or connecting it through internet using the different modules available like ESP8266 is one of the modules. So that's just a Wi-Fi shield with all the features of the microcontroller in it. So these are all the interfacing technologies that the microcontrollers are accustomed with to get a custom program loaded. Going forward, So, motor drivers. Briefing it up, do you remember we talked about controllers? There were two sectors, controllers and processors. So, processors and microcontrollers are likewise, but not all controllers are microcontrollers. So, controllers, what they do, they help us decode the information from the sensors to the microcontroller or processor, or vice versa. It sends a signal from the microcontroller to the sensor, which can be an actuator or an output device, to work accordingly. For instance, an IR module takes the information from the external environment, so be it degree of reflectance or presence of an obstacle, these can be the practical scenarios. So the IR module takes this information and feeds it to the microcontroller through an IR driver. So an IR module does not only consist of an infrared LED and a photodiode or a photoresistive LED. These can be used. So these feed the signal back to the LED drivers. So there are IR drivers which you might not be familiar with because people don't use that anymore, and those are made into more compact modules these days, and it comes in as a single package. So you might not be aware, but there is always a driver where a sensor comes into play. So what are motor drivers? To be very specific, we are talking about motor drivers because we talked about the locomotion and movement of robots, right? So we also need to decide how the autonomous robots need to perform, need to move, need to follow the instructions so as to take note of the external influencing factors and react accordingly. So the motor drivers are types of controllers or interfacing medium between the microcontroller and the motors. So what this does, this particular driver is called L298N. This is quite a very basic type of driver which most hobbyists use in their prototypes, and on a wider aspect, it's one of the worst drivers because it has very less current efficiency and heating problems, and it can also short out if applied with a greater voltage than 12 volts. You can also get it running on 16 volts, but that will eventually fry your controller. So basically what this does is, if you look closely, I think it's quite visible. In the front part where there are 3 blue screw terminals, beside that there are 4 pins visible, right? So these pins are the control pins for 2 sets of motors. On the left and right there are 2 separate screw terminals where the motors are connected, and on the front part those 4 pins help to control these motors individually. These need to be connected to the microcontroller with wires, and that helps to decide which motor to turn in which direction and with which speed. Everything will be controlled through this driver. There are multiple motor drivers present in the market. This one is one. Another one can be L29GB, which is just a lower variant of this with a lesser current efficiency and current capacity, which can also be used in prototypes like Mars rovers, for example, alternate vehicles, or a simple line followers, obstacle avoidance robots, anything that involves 2 motors and a 2-wheel or 4-wheel drive system. So that is quite some brief about motor drivers. Next coming up, let's talk deeper into one of the most commonly used microcontroller units, abbreviated as an MCU. This is an Arduino. How many of you are familiar with this? Have seen anywhere? So someone from there, can you pass the mic there? So can you please share what was your experience with this?
The first one we bought was actually not working because the LED was not blinking the first time. So we had to change it, and we were trying to make a line follower with this.
What sensors did you use?
IR.
So how many IR sensors did you use?
2.
Okay, so let's get down to basics. What type of signal does the IR sensors let out?
Infrared.
No, not that way. I mean, what signal does it feed into the microcontroller? Is it analog or digital?
I think it's analog. I'm not sure.
Can you support your Arduino? Then why did you randomly choose analog? I mean, you must have thought something.
Actually, when we were doing this, we studied about all this, but then I forgot.
Okay, so basically, yeah, you can sit down. So basically, what he's trying to say is he wanted to implement a prototype of a line follower robot. We might be having a small demonstration of that. So an infrared LED or IR module lets out different types of signals, both analog and digital, towards the microcontroller. Because the driver present in that helps to decide the intensity of the light being reflected back, as well as in a decision making way if the light is reflected back or not. So in the latter case, it will be a 1 or 0, a digital output, and on the former case, it will be a value from 0 to 255 as it's an 8-bit analog to digital converter present in the Arduino, so it can only read from 0 to 255 values. Anything greater than that, it has to be constrained. Under that, there are already methods defined in the Arduino IDE. The language it uses is embedded C, so anyone familiar with C programming or Java programming might find it easier to code in the Arduino IDE. So keeping apart, let's get into the basics. So in the picture visible, the partner is not visible, but you know that long black thing, don't take it otherwise, point to be noted. So whatever, so that is the microcontroller unit. Jokes apart, let's come back to the topic. So that is the basic microcontroller. Main microcontroller is that chip, which looks like an integrated circuit, typical one. And anything outside that, you can see many assembly components, many pin headers. Those are just used to filter out signals going in or coming out from the microcontroller. That does not play any active role in deciding what the microcontroller does, but eventually it filters out any kind of noise. It keeps track of any incoming voltage levels, any outgoing current levels, and it helps to keep the microcontroller protected, because any kind of voltage spikes can fry the microcontroller. Once you start working with these, you will get to know that Arduino functions in a very low voltage range. It has to be greater than 5 volts and very safe under 12 volts. Even though it has a 5 volt to 12 volt integrated circuit for maintaining the voltage under 5 volts, it can still operate on 12 volts, but anything greater than that, that will just fry the microcontroller. So anyway, this can still be replaceable, but if you just pull out the IC from its socket, it has a socket in it. So you pull out that IC, you buy that same one from the market, and you plug it in. It can be done, but there's a catch. You get it home from the market and you plug it into the computer with the USB, and you see it's not detected. Why would it be that? I mean, you just bought an aftermarket IC, right? Why would it not function like that? Is it not being able to access the serial interface or any USB interface? Or is it that it's just blank? It does not have anything on it. It's just a piece of hardware. What can be the odds? So let me tell you, when an Arduino, when you buy this full package, it comes with a default bootloader. The same bootloader that allows your computer to have a BIOS screen. Without a BIOS screen, can you get to know what components are connected to the computer if no operating system is installed? How do you get to know how many fans your cabinet has, or how many I/O devices are connected to your computer? All this information can be gathered from the BIOS screen. So the BIOS works on a default bootloader that is directly related to the CPU architecture that is being used. And also it has to be compatible with the motherboard chipset so that the processor interacts with the motherboard. Similarly, the Arduino also comes this particular chip called ATmega328P or 328 PPU. There are two variants. It's just a model number is different due to different frequency, but it actually does not play any active role in that. So what it has is a default bootloader is present that lets your computer know that it is an Arduino IDE, it is an Arduino board which is detected inside the Arduino IDE. But if the bootloader is not present, how does your computer know? It will never get to know what piece of hardware, what junk you just plugged in. It can be just a blank USB cable with nothing on the other side. Or it can be manipulated to make the computer understand that, yeah, it is a device, but it's actually not, you're doing some crooked things on the other side. So it has to have a bootloader. So when you plug in a blank IC, it can be a cumbersome process, it's quite difficult for beginners, but let me tell you, it can be done, you just have to get another Arduino. You get the point there, you don't buy just the chip to replace it, you buy a full Arduino. Because it's not worth whatever effort is required to plug the bootloader back into the IC for interacting. So that was quite informative, and rest of the things, general information you can see on the slide. There are 13 digital pins, 1 to 13. Generally 0 and 1 pins are not used because if you can see there are RX and TX written. So RX and TX basically communicates with the USB's data in and data out. So if you plug in anything on that, it will cause the communication to disrupt, and eventually it will give an error, unable to upload, or error uploading the program in the board. So never try to, you can use those pins if you run out of pins, but try avoiding using 0 and 1 pins when you start prototyping. And apart from that, on the bottom part you can see A0 to A5, 6 analog pins that has the 8-bit A to B converter, analog to digital converter. So it can read values from 0 to 255 analog and convert it to 0 and 1 digital. Rest of the pins refer to 5.5 5 volts, 3.3 volts. There are ground pins, there are V-in pins. So let me be very specific. The V-in pin that you see just to the left of A0, the V-in pin is basically a variable voltage input pin. So you can put in any voltage between 5 to 12 volts in that pin, and it will be regulated by the onboard voltage regulator. So as long as it is below 12 volts is fine. Anything above 12 volts will fry that regulator and render your board useless. It can be repaired, but it's then again a tough process for whatever price you are getting these Chinese clones in the market. It's not worth. So if you just try one, go ahead, buy any. So you might be wondering that, yeah, you told us about the Arduino, it's a hardware. So how do we plug in decision making abilities in that? So for that, similar to any coding IDE, like you have used, what all IDE do you use? Speak up, anything. What IDE do you prefer using for coding? Any computer science students? Are you all from biology? That must be very saddening because most of the things I said, yeah, what IDE do you use?
Started with BlueG, but now I am using VS Code.
Okay, so here, as you said, VS Code is quite a fundamental IDE. It has many of the inbuilt features to debug as well as code in different languages. Quite a versatile IDE. So similar to that, Arduino has its own IDE. It uses embedded C as its language, so it has both an object-oriented and a non-object-oriented approach. Similar to any other programming language, you can define strings, variables, functions. Function calls are quite same. So the Arduino IDE mainly uses two methods: void setup and void loop. What does it sound like? What does void setup do? It basically sets up the microcontroller and helps it know what all pins are there, what all devices are connected, and which pins to actually work with as inputs and outputs. As long as you define the pin, yes, let's take an example, you want to control the brightness of an LED. So it will be a variable output, right? So which pin would you like to plug it in? Is it one of the digital pins or is it one of the analog pins? So it will be one of the analog pins, right? So there you can vary the output voltage, output pulse even. So it can bring about a difference in brightness of the LED. That will be more convenient. On contrary to that, Arduino has the ability to decode analog signals from the digital pins also, but digital reading from analog pins will lead to some errors. So don't try to do a digital read from the analog pins when you prototype, but rather if running out of analog pins, you can always try analog reading from digital pins. It's just a piece of information. So the Arduino IDE has two default methods, void setup and void loop. What the void setup does, initializes all the variables and lets the board know for the first time setups. And void loop actually runs iteratively an unlimited number of times when you turn on the board. After it goes through the void setup function, the void loop keeps on calling itself repeatedly, and whatever function, whatever methods are written and called inside the void loop will get repeatedly executed over and over again after you start the Arduino board. Moving forward, this is an example of an Arduino code. It says bling the built-in LED that is generally connected to the pin 13, digital pin 13 of the Arduino. Like any other coding language, you can use double slash to comment out a single line, and the same convention goes for slash star, then star slash to comment out bigger paragraphs. So, what can we see in the void setup and void loop? Pin mode. What does it sound like? Pin mode. Setting the pin mode, like what it has to do, an input or an output device. It has to let the board know, right, before functioning with the digital pin. So pin mode, the format is simple. You specify the pin number, comma, then you mention output or input. If I had written input, it would have waited for an input signal. If you have plugged in an LED on an input, it just won't function, right? LED has no output capabilities. So the pin mode of pin 13 is set to output. As I said already, pin 13 already connects to a built-in LED, that is the status LED on the board, and it is set to output through the void setup. So first, when you turn on the Arduino board, void setup gets executed once, and the board knows that I have to react to it such that pin 13 is set to an output. Then what happens in void loop? Digital write parameters are the pin number and a status, high or low. So why does it say high or low, and why does it not say any other value for adjusting the brightness? As you can see, we have used a digital write method. So what digital write does is, it sets the value to 0 or 1. We could have used high and low or 0 and 1 eventually. So the status of the output pin 13 is set to digital high. Digital high refers to positive 5 volts, and on the next line, digital write 13 low sets the value to digital low or a logical level of 0 volts. So eventually the LED is off. So what does the delay function do?
Creates an interval.
Can I please stand up? Whoever said that?
Creates an interval between the high and low input.
Creates an interval. So what is the value 1000?
1000 seconds.
1000 seconds.
1 second. That is 1 second.
1000 milliseconds means 1 second. So any kind of timer related input in the Arduino code, it is already by default in milliseconds. So yeah, you are right there, but that unit was a bit off. So what delay does is, it adds an interrupt or an interval between two consecutive statements. So after digital write 13 high, that means the LED state is set to logical level high, logical level 1, which means plus 5 volts is being supplied to the LED. So the LED will glow. For in the meantime, a delay of 1 second is added, so it will stay illuminated for a length of 1 second. After that, when we put in digital drive 13 low, the state of the LED will be turned off, and since logic level low, digital low is being applied, that is 0 volts, so the LED will turn off. It will stay in that off state for another 1 second. In those types of boards, the board can actually take more than 90-degree turns and keep the board on track even when there are steep turns, and the board can be very fast actually. So, as I mentioned, the PID algorithm, has anyone heard of this anywhere? Someone was working with a line follower. You ever got to understand or got acquainted with what is PID? Anything marginal ideas? You can see a graph plot type of thing going on with the values increasing. Can you see those values by the way? It's too small. So what a PID algorithm is, it's a decision making advanced type of algorithm that helps to let the system know what is the total error from the designated path and how much it has to, at what rate it has to react to keep as close to the designated path as possible. For instance, you can check the animation here. There are 3 variables called KP, KD and KI. These refer to each of the letters in abbreviation of PID, which stands for proportional, integral and derivative. So what proportion consists of? Proportion is what is the respective change compared to the last change that occurred, or even from the start position. What is the comparative change? That is the proportional change. Totally as simple as that. Whatever you know of proportional in mathematics or physics or anything, the term applies everywhere. It's the same like that. Integral is what is the total change that your system took place with, so as to keep it on the designated position or as close to the designated position. So ideally speaking, integral change should be very less or as accurate as 0, because you want your system or a simple line follower board to stay stuck on the straight line, right? You don't want your board to deviate from the line. So as long as the integral is kept 0, the board will try to correct itself repetitively so that it stays dead center on the line. In an ideal system, the integral is kept in the range of 0.0001 to add in a bit of error so that the bot can get some flexibility to react to the abrupt changes, but ideally it should be 0. And last but not least, derivative. So derivative is same as whatever you have done in mathematics, ddx of y, where y is a function. So derivative takes care of what should be the rate of change. Proportional we talked about what is the comparative change with respect to the last change or with respect to the start position. Derivative is how fast the bot or the system should react to that change. If the derivative value or KD value is set way too high, the bot will be snappy as hell. Like if you just move it away from the line, it will go in full speed to get nearer or closer to the line as possible. But if you keep the derivative lower or maybe a considerable value, it will gradually try to make the change and react accordingly as the P value changes. So P and D are directly related, and I just contributes to the whole system to decide what the total error is, to make sure the target or the initial point is taken as a frame of reference and tries to keep the system on track. So as you can see from the graph, as the Kp value increases, the amplitudes of oscillation increases. Can you observe that? What does that mean? So more Kp or proportional constant is fed into the system, the system will try to make larger changes and compensate less for any kind of small errors. So it will take on a longer path to attain its final position, or it will react very less compared to the last position. Then next comes KD change. When the KD change comes in, you can check that the rate of change of P decreases a bit. As the KD rises, the rate of change increases, but the total change compared to that KP decreases. KP value doesn't decrease, but the change in that eventually gets flattened out. On the other hand, when the Ki value increases, even when the Kd value is not plugged in, Ki tries to decrease the total error achieved in the system. In that way, the system will be made aware of that yes, you have deviated enough from the system and your total error is this. For that, you have to react to change accordingly as per the Kd value, because D specifies the rate of change it needs to make compared to Kp, when Kp just makes sure that it takes the turns quite steeply and tries to stay closer to the designated path. So the graph is quite convenient to see, and you can see practically what each of the values do. And about the values, these needs to be experimentally found out. If someone says that yeah, you make this line following bot, you just plug in the Kp values and Kd values that I just sent you, and the bot will work fine. And you just bought all the components from the market, you soldered everything properly, you connected everything as per the schematics, and you just upload the code, and the bot is oscillating vigorously on the line or not even staying close to the line. And then you get to complain to your friend that yeah, whatever value you sent, it's not working. Either you are stupid enough to copy that value, or you have not made the bot identical to you. That should be the case. So every single part of Kp, Kd and Ki should be experimentally decided. Like for instance, bringing the line follower case, the speeds of the motor are decided by the analog PWM values. That varies between 0 to 255. So at what range do you wish your error to be? Within 0 to 255, I mean within 100 range. You won't plug in 1000 range when the maximum speed can be 255 or the maximum analog value will be 255. In that way, it will be again constrained to 0 to 255, and your system will not respond because 1000 is not a value in that. So eventually, you will have to decide all those Kp, Kd, Ki values experimentally, and all those genius coders out there who are already working in these technologies, they are putting in enough efforts to make the calibration and setting of PID quite convenient for geeks and noobs like us who are just starting out. So for a demonstration purpose, the effect of Kp is demonstrated. I think there's no internet access. Okay, it's working. So whatever you're seeing there, the sensors are being calibrated as this is a multi-sensor board, and it's quite an advanced type of board. So as you can see, the Kp value is specified, but this will work only for this particular board. If you make the identical board with exact parts, then only this Kp value will work. But once you start changing the materials, like yeah, you got the chassis, but I'm not being able to procure it from the market, so I'll make one with cardboard or a tiffin box or something like that. See, eventually you will get to do these kind of things. Like once you start buying stuff from the market, it will get too expensive. So you will have to learn to use household materials and make use of things that are not meant to be used for a chassis or a wheelbase or anything like that. So there it goes. Like Kp, Kd, Ki values are already very delicate to make the board change, to make the system change from the error position and eventually achieve the designated path. And every individual device has a different Kp, Kd, Ki value. Even though you make it identical, even though you space the sensors equally, or you use the same amount of sensors, same number of sensors as someone that showed you in the video, you will most probably not get to work with same type of KPKD values. Eventually, you will have to work on tuning all these things, and nothing beats experimental. Right. So moving on. So that was quite much about the autonomous bots. You got the basic idea of a microcontroller. You got the practical examples. You got to see a demo of the bot being played. And let's move forward to a more advanced aspect of both autonomous and manual systems, Internet of Things. What do you understand by Internet in general? Don't say that Internet service provider wala Internet or your Wi-Fi means Internet. Anything, any vague idea on what Internet means? Wrong, right, doesn't matter. What do you understand by Internet?
Global network.
Yeah.
International network.
Can you repeat? I couldn't hear you. Can you give me the mic, please?
International network.
No, actually, that is wrong. Pass on the mic behind.
Is a network which helps to connect us to the world.
So basically, it's a medium of connectivity, right?
Yes.
It will act as an interface between connecting two or multiple types of devices. Be it devices, be it sensors, autonomous systems, humans to other systems. Internet just is an interface. So what Internet of Things include here? Internet of Things can be referred to as collectively connected systems consisting of both autonomous and manual devices or systems that can work in sync with each other, following a particular line of information or following a particular source of information to act accordingly, which in unison produces a particular output or a desired output that will eventually be influencing the human lives and maybe making it easier or convenience will be increased. So, getting to know IoT devices, it will be quite thrilling to see that by the press of a button on your Android phone, the color of an LED can be changed. It's quite thrilling for the human to perceive this. So, this is as basic as controlling an LED to as advanced as getting health statistics on your phone. So there are multiple smartwatches available in the market that uses different health sensors and gets connected to your phone over Wi-Fi or Bluetooth and eventually sends the health data to your smartphone device. So that is plainly an example of IoT device. So to achieve IoT, different types of embedded systems and standalone systems are used. The most basic and most entry-level thing being the Raspberry. I already mentioned it. So, if anyone remembers, what did I talk about? What did it have? What is a Raspberry Pi? Is anyone accustomed to it? Yeah.
It's a full-fledged computer in a miniature scale.
So, right you are. It is a standalone computer in a very small form factor. It has the full capacity to replace a very low-spec desktop computer, since a monitor can be connected. IO devices like keyboard, mouse, printers, scanners, cameras, everything can be connected. It also comes with a default camera of it that needs to be separately connected, but it is only compatible with the Raspberry Pi. So, for controlling IoT devices, you need a brain, and Arduino's microcontroller is not enough of a brain that you need to control the IoT devices for. There, Raspberry Pi comes into picture, which has a full-fledged computing capability, runs an operating system, has a 64-bit processor. It is working on the ARM architecture. So, using this Raspberry Pi, different basic to advanced level IoT systems can be implemented. For instance, it can be as basic as I just mentioned, changing the color of an LED with the click of a button on your Android phone, and as advanced as keeping the LEDs synced together all around the house and turning them on and off accordingly as per your presence in that particular room or particular hall. So these can be achieved by using Raspberry Pi. Since it is a standalone computer, once you load the instruction set through the, mainly we use the Linux command line. So either it will be a Python script or any bash script running on the Linux platform, or it may be programming the general purpose input output pins to set the particular instruction sets for each of the IoT compatible devices connected. So here also comes one catch. How do you know a device is IoT compatible? Number one, it must have a signal pin or a signaling interface or at least a driver or controller so that it can accept any messages, any information, any change of data from a microcontroller or a processor. So if you say that I have a motor that has two terminals, it can run on only one speed if connected to a battery. But if the motor is hooked up to an encoder, which many advanced processors use, generally an encoder is connected to the systems. So what an encoder does is, it converts the signals and data pulses from the processor or microcontroller to the readable format so as to manipulate the device connected to. So when you find out that an LED color is being changed, there is certainly some piece of hardware or some piece of circuit present in that can interact with the interface, be it Wi-Fi, be it Bluetooth, and it can take in the information or data pulses or signals sent over the Wi-Fi, and it can decode that so as to change the color and or respond accordingly. So every device is not IoT compatible, but to some extent it can be made smart device, which is the common term for IoT devices, with the involvement of some piece of technology or controller or modules too. So when starting off with IoT, I would suggest that you check out some open source platforms first. For instance, if you want to make an interfacing between Android and Raspberry Pi, or maybe even an Arduino, you can use the Blink app. It's BLYNK. You can check out your Play Store for that. So Blink is an open source development project. It helps to connect to devices, microcontrollers through Wi-Fi or Bluetooth, and it can act as quite an efficient platform to control or regulate or get the output from one of the devices to and from your Android phone. So basically, as basic as it can be and at the same time interesting, you can make a Bluetooth controlled RC card using the Bluetooth modules as interfacing between the Arduino and the phone, and the basic four-wheel drive and motor drivers and batteries that we already just discussed to control the movement of the car. So this is achieved by using the Blink. Blink app is quite conventional for usage, and it's quite flexible for beginners because it provides a wide scope of applications and involvement. It has all types of inputs like press and hold a button. You have seen different websites, right? You just tap, hold a particular space in the page and it reacts differently. You toggle a button on and off and it reacts differently, or it takes you to a different page. All these interactions can be set up inside of the Blink app, and it is as simple as a drag drop interface. So you do not have to worry about any Android coding or any in-depth app development stuff to achieve this using Blink, because everything starting from a button to a slider to a graph plotting interface, everything is available in the Blink library. You just have to download the app and drag and drop the components in the screen. So this can be an entry to the IoT world. Then you can move on to using Raspberry Pi. Raspberry Pi can connect to your home internet, and if your device is Wi-Fi compatible, if it can, as basic as Amazon Alexa and Google Home type stuff. So these can be communicated over with Raspberry Pi. All these IoT devices, all these smart home appliances, starting from remote controlled fans and lights to turning off the water pump or likewise, you get the sense. So these can be achieved by using programming the Raspberry Pi accordingly. For that, for basics, I suggest you to start getting into Python, because eventually you will be using Python scripts to run into the Raspberry Pi, and also get accustomed with the command line interface of the Linux, because it runs the default OS for the Raspberry Pi is Debian, so it runs on the Debian interface. You can also install other Linux distributions like Ubuntu or Kali. That will be a bit advanced, but I would suggest not to go in depth from the very beginning. And also these are available quite in an affordable range, and you can buy some of the older versions just for prototyping. You can start off prototyping, and experimenting is never a failure. You will fail through experiments, but at the same time you're also getting to learn something. So whatever I discussed that might not be as easy to understand, or you might not be able to picture that, so here's a small demonstration. So Supratik, where is this video kept? Can it be played from here? So we'll play a video to demonstrate how the smart home appliances work.
Hey Google, good morning. It is 7:15 a.m. Currently in Fort Mill it's 69 and cloudy. Today, there will be scattered thunderstorms with a forecasted high of 84 and a low of 65. Here's the latest news.
Hey Google, make me a hot coffee. Hey Google, good night.
Thank you.
Yeah, so now it's revealed. You can see it on the screen. This is going to be a quiz based on some general trivia and some questions based on topics we discussed today. And yeah, the winner of the quiz will get an Amazon gift card. So let's try to participate actively in this. Okay. I'm going to ask the volunteers, the 4 volunteers who are here for hall moderation, if you can come up to the front and keep a note of who raises their hands first. So what you need to do to answer is raise your hand up. Okay? If you want to answer, raise your hand up nice and high so that I can see it from you. And the volunteers will tell me who was the first person to raise their hand, and they will get to answer the question. And Shohit, are you present here? Yeah, please keep a note of the points. Okay? Cool. So we're gonna get started right now. The first question. This is based on what Pritamda was discussing a little while ago. What is the microcontroller used in Arduino Uno? So I want the name of the microcontroller itself. It's an alphanumeric name. So give me the name of that. Anyone?
Keep track of the time.
Anyone? You can guess. Someone's raised their hand.
PID algorithm?
Sorry?
PID algorithm?
No, I want the name of the microcontroller itself. Okay, no problem. I think no one gets points on this one. Okay, someone's raised their hand. What?
It is ATmega something, capital 80 mega.
Yes, ATmega what?
38 some. 3 8 something.
Cool, good answer. Someone at the back?
Actually,
Yeah.
I know the value. It's 383. Omega 3383 TZ something.
No, I can't take that answer. Sorry.
Okay, sorry.
So I think it goes to him. What's your name? Sorry. Okay. So he gets a point for this question. Please take a note of this.
My name is Otulanto.
Otulanto. It's the Atmega 328. This was written. I'm not sure if we're going to discuss this, but it was written on the slide. Right. So the second question, once again, this is also a question from the session today. To achieve variable speed on different wheels, which type of drive is used? So these are the types of drives that were, I think someone raised a hand over there. I saw the hand go over first. Volunteers, can you please confirm? Yeah, give the mic. Okay, so 4-wheel drive, 2-wheel drive, differential drive, and chain pulley drive. Differential drive. That is the correct answer. Differential drive gives you variable speed on different wheels. Yeah?
Do one thing before answering, just say out your name loud.
Okay, so this is a trivia question. Oh my god. Okay. Let me at least read this out. In 2017, Saudi Arabia made history by granting legal citizenship to a humanoid robot, making it the first robot to be a citizen. Name the robot we are talking about.
Sophia.
Nice. So yes, the answer is Sophia. I think there was an event in Calcutta as well where she was demonstrated. Technically. Nice. So yeah, that's Sophia, the first robot to be granted citizenship. Next question, once again from the session. Which part of the robot provides motion to the end effector? The options are controller, sensor, actuator, and none of the above. What's the answer?
Somebody said that actuator.
Actuators. Right. Good job. I think you answered 2 questions already, yeah? So yeah, the correct answer for this one is actuators. Moving on. Oh wow, okay. This is not my question, guys. That's a disclaimer. Yeah. Name.
The one who names all these words gets the point. Otherwise, no points on those.
Yeah, so it's Preetham's question. He makes the rules for this one. Yeah, anyone wants to answer? Try answering even if you don't know the names of all the words. You might not get the point, but still try answering. Do we have anyone who wants to answer?
Come on, half भी बोल दो चलेगा.
हाँ देख half भी बोल.
अच्छा 2 चलेगा.
2 चलेगा. Okay.
2 out of 4 should be done.
1 is TT and 3 is Android.
Which one?
3.
One more try. Try something else.
Anyone with you?
My name is Rajoshi Gupta. Number 1 is TT and third is R2D2.
Nice. R2
Versus from this one.
And the others are HAL 9000. This is from 2001: A Space Odyssey. If you haven't seen that. And Sunny from iRobot. Okay, another trivia question. More than 1 million industrial robots are in use today, but nearly half of them are employed by a single country. Which country are we talking about?
Japan.
Nice.
Name. Ronic does.
Japan is the answer. It uses nearly half of the industrial robots that are in use today. That's pretty insane. Probably the simplest question on this quiz. In 2013, a space research organization launched a Mars orbiter mission with a budget of 73 million US dollars, making it the least expensive Mars mission ever. Which orbiter are we talking about?
Mangalyaan.
Yep, that's the right answer. We are talking about Mangalyaan. Okay, the last question of the quiz. This is from the session. So, accelerometers and gyroscopes are examples of what?
Sensors.
Yes, that is the right answer. So, these are all sensors as was discussed in the session today.
I think we have a tie, right?
Do we have a tie?
Yeah.
Between?
Between.
Okay, the two people who are tied, can you please stand up? Okay, so your question, this is from the session. It's a simple question. Whoever raises their hands first gets to answer. What is the full form of PID?
Proportion, integration, and derivative. Sorry.
Yes, that's the right answer. Congratulations, what's your name? Samvit, yeah. Congratulations to you. You are the winner of today's quiz. And with that, we are coming towards the end of the event today. Before we have the live demonstrations of the bots, I'd just like to thank all of you for coming today and staying the whole time. Because that's what matters ultimately. Well, this being the first offline event of GDSC RCCIIT, I'm very happy to see that we surpassed 70 registrations in the first day itself, and a lot more people were enthusiastic to come. And yeah, I just hope we get we can organize a lot more events in the future, offline and online, and we can have a lot more people coming together and learning. So yeah, with that, we're going to just take a few minutes for setting up.
The drive mechanism and what kind of movements can be achieved with this. And any two volunteers can be accepted. Will anyone try to volunteer in this? Just to get the idea.
One more person?
One more. Yeah, you can come on. So I'll be explaining the drive mechanism and so he will be driving this and I will just communicate what are the movements. So we are using two DPDT switches. We are using two DPDT switches in this. One switch is for each of the motors. So as you can see, every kind of movement, forward, backward, left and right can be seen. The motor is causing some noise because it's olden and the gears have worn out. These are plain plastic gear motors. So do one thing, press one button at a time. So pressing one of the buttons can move one motor independently. I put it back. So each of the motors can be individually controlled side to side. So very small rotations can also be achieved. We can also move it rapidly by pressing two alternate buttons. So our volunteers, would you like to try this, to give it a try? One of you come on. So our colleague just explained to him.
পিতাম্বর মুখ কেটে যাচ্ছে পিতাম্বর মুখ কেটে যাচ্ছে
So each of the buttons on the left and right are correspondingly for left and right motors. Press it forward, the motor will go forward. Press it back, the motor will go back. And you can quite press hard enough, no worries, it will not break, it will already broken. So you are getting the idea of its movement, right? So what kind of movement we can achieve by designing a board from two-wheel drive, and the similar mechanism can be achieved in a four-wheel drive. So guys, what is the disadvantage of this two-wheel drive? Anything, can anyone come up with? What can be a disadvantage? Come over. Anything, anyone? One disadvantage of two-wheel drive. Very visibly, the car. You raised a hand.
Like it won't be as fast as a four-wheel drive car.
Yeah, that is fine, but related to the movement, what hindrances do we face? Do one thing, take the car forward, take it backward. So very visibly, it does not come straight forward and backward, right?
Yes.
So the motors are not reacting synchronously at the same time.
Yes.
So this can be overcome by which drive mechanism?
Four-wheel.
So the four-wheel drive and two-wheel drive differs only at number of motors. Nothing else is different. It can only be managed with a differential.
Yes.
Because the differential drive can allow the motor wheels, each of the wheels on a single axis, to react differently to one speed. Eventually, when we apply the speed for backward or forward motion, the differential drive system will even it out and put the same amount of speed to each of the wheels. In that way, the car can go perfectly forward and perfectly backward at the same time. Here, in this case, when implementing a two-wheel drive, we can see how hard we try doesn't matter. We cannot press two buttons at the same time. Try taking it forward. Whatever he does doesn't matter how fast he responds or anything. It won't go in a straight line. Take it back. So it's not getting in a straight line, right? There can be other hindrances like hardware issues. Yeah, one of my motors is bad, I already mentioned, but that does not add up to the system, that does not add up to the drive mechanism. Hardware errors will always be there. But end of the day, it matters what type of drive we are following for manual boards. Because in case of manual boards, the ability to drive can be treated as a primary thing to get a grip at, but at the same time, the hardware should be compatible enough, right? So you all got this demonstration from this. After that, we will try to make some changes on the same board because we don't have enough resources to make different boards for manual and autonomous. We'll make some changes and let's take a 5-minute break. I guess the operation is clear from this, though we have hardware limitations. See, the bot took a wider turn, so that means the KP value needs to be calibrated, so it can react to smaller changes faster. It still tries to take the sharp turns, and 90-degree turns can be the optimal value to test for PID success or failures. Yeah, so kind of going right at this point. Okay, so this has been the best run till now, and it over. The quality of sensors as well as what motor driver we use, whatever logic we have written in the code, everything counts for the responsiveness of this bot of the line. So if anyone wants to take a closer look and know about the parts, a few of you can come forward.